became a reality.
Man had fiddled around with the concept of the submarine for hundreds of years.
All kinds of prototypes have been built, but they all hit the same stumbling block: how to devise an effective means of propulsion. In 1897, an Irish-American inventor had a flash of inspiration.
And then along comes a man called John Philip Holland, who had the notion of marrying the internal combustion engine with the battery. And therein really lies his genius.
Here's Holland 1, a product of that genius. Built in 1901, it used a petrol engine to drive it on the surface. But this engine did a second job. It charged an electric battery, which in turn would propel the submarine underwater. Holland's early designs had been driven by a desire to build a weapon to attack the hated Royal Navy. But his genius was such that even the British government put aside their reservations that these were ungentlemanly machines. Holland 1 was the first ever Royal Navy submarine. But its great strength, its petrol engine, was also its Achilles heel.
Well, this is a little trough full of petrol. Very volatile, gives off lots of fumes which affected people on board the submarines, catches fire very easily. A lot of explosions and fires on the early submarines.
A safer, more stable fuel was needed. The obvious candidate was diesel.
And this is a trough of diesel. The important thing is it gives off much less vapor, it's much less volatile, has a higher flash point.
It takes the concentrated flame of an industrial blowtorch to set it alight. First used by a French submarine in 1903, by World War I, diesel was the fuel of choice in every Navy's submarine fleet. But it was the German Navy that would really exploit the diesel-electric engine. By World War II, their U-boats had evolved into highly reliable, deadly submarines. They wrought havoc in the Battle of the Atlantic. But even the U-boat was still reliant on electric batteries for underwater propulsion.
The big limitation that a diesel submarine had was that it had to charge its batteries. It was totally dependent, at the end of the day, when dived, on its batteries.
And to recharge those batteries, the submarine had to come back to the surface every 24 hours. The diesel engine that charged them needed to take in air.
The time that a diesel submarine was most vulnerable was when it was recharging its batteries.
Underwater, the submarine was almost invincible. On the surface, it could be a sitting duck. By the end of World War II, the days of submarine supremacy seemed numbered. Then came a new kind of fuel, nuclear power. With it, a submarine need never surface again. The American submarine Nautilus was the first to use nuclear propulsion.
In 1955, when USS Nautilus made the famous signal underway on nuclear power, it was announcing that the world has seen its first true submarine.
Nautilus marked a step change in the way a submarine could be used.
With the arrival of nuclear submarines, you've got a submarine that was effectively a true submarine. It really was independent of the air, of the atmosphere, and that gave it a tremendous capability.
This is one of Britain's first nuclear submarines, HMS Courageous. Built in the late 1960s, its energy source was equivalent to the output of a power station. Rupert Best was one of the Royal Navy's nuclear pioneers. He was a key member of Courageous's construction team and went on to captain her during the Falklands War.
The thing that really struck one in seeing her launch and then joining her was how very much bigger and a much more substantial vessel she was than anything I'd served in before. And that size and, of course, the capability of nuclear power gave her qualities which a conventional submarine would never have had and never could have.
Submarine propulsion had been transformed. With unlimited power, the submarine could go anywhere in the world, and for the first time, it was faster than a surface ship. Now, the ultimate submarine was becoming a reality. Of all the threats the submarine must face, there is none more dangerous than the sea itself.
They live in a naturally dangerous environment. The sea is just waiting to get in, so you've got to keep her out.
A submarine's hull has to withstand the enormous forces of water pressure. The deeper it goes, the greater the strain. At 200 meters depth, there's a force of 150 kilograms pressing in on every square centimeter of the hull. At 500 meters, this is more than doubled. Submarine designers had always built their hulls to a safe theoretical working depth. But what would happen if a submarine went beyond this limit? In 1945, they decided to find out.
At the end of World War II, the Royal Navy took a number of redundant S-class hulls and literally put them into deep water to wait for the moment that they crushed.
These dramatic tests gave us startling insights into the limits of the pressure hull.
You had an absolute percussion. It was like a gun going off. Literally went from creaking pressure to snap. The whole thing imploded. In one sense, from a submarine point of view, that's quite reassuring. At least it'd be quick.
Paul Morehouse builds submarines to order. The thickness of the steel he uses depends on how deep the submarine needs to go. The inner core of the submarine, the pressure hull, has to be able to withstand it.
This pressure hull here is designed to dive to 300 meters, and it's made of steel, high-grade steel, which is 16 millimeters thick. And it needs to be all of that because the pressure outside is 30 times as high as it is normal atmospheric pressure.
But weight limits how thick the steel can be.
Sometimes people think that you have to have it heavy to make it sink, but in fact we have to keep things light because we want to go as deep as we can.
The solution to the strength-weight equation is to make the pressure hull round. Roundness distributes the water pressure evenly. But the masterstroke came in the early 19th century with a deceptively minor addition: metal ribs.
If we didn't have these ribs, then it would be a little bit like a Coke can. It's very easy just to squash a Coke can because it can't resist outside pressure. You can very easily put a dent in it. And if you didn't have any ribs, it would be the same with a submarine hull. It would be easy to put a dent in. And as soon as it started to go, then it would collapse all the way.
So just how much difference do these ribs make? This is one of the largest pressure chambers in the world. Fully flooded, it can simulate sea depth of 1,000 meters, beyond the pressure that most Navy submarines can withstand. Two steel pressure hull models of identical thicknesses are about to undergo a searching examination. One has ribs. Both will be tested to their limit. At 100 meters depth, both models are intact. At 200, still no sign of implosion. Then, at 300 meters, the ribless model collapses. The ribbed vessel is yet to show any sign of stress. Then finally, at 400 meters, a spectacular double collapse. The test models were identical, but the addition of 3 small ribs enabled one to go 100 meters deeper before imploding. So the ribbed cylinder gives the pressure hull the strength it needs to keep out the phenomenal force of the sea. But a submarine needs more than just strength and speed. Control is vital. It has to be able to maneuver underwater. To do that, it needs wings. Submarines are instruments of war. They rely on stealth and surprise. They need to be underwater for these qualities to shine.
make a submarine go underwater and to control its depth is a little bit more complicated than the popular assumption.
To submerge, maneuver underwater and surface, a submarine needs control. Early submarine designers grappled with the problem of how to control their submarines. To submerge was easy enough, but to return to the surface, another matter. Whatever the shape or size of the submarine, the big problem was getting the weight right, because this determined the buoyancy. Even today, this is an issue.
The weight of the submarine is absolutely critical. We weigh all the equipment that goes on board. We even weigh things like pipe clips. We know how heavy electrical cable is by the meter. So we know how much weight we're putting on the submarine. And there is a whole department which concentrates solely on weight control, because that will define its buoyancy, its stability, and all these other naval architecture parameters.
By the late 19th century, submarine designers had learned that by attaching ballast tanks to the hull and letting water into them, they could make the submarine submerge. For the diver, his ballast tank is the jug. But to return to the surface, the water had to be pumped out. This was very difficult with manually operated ballast tanks. The breakthrough came in 1888, when a French submarine used compressed air for the first time to force the water out. This meant that at last, a submarine could determine precisely when and how quickly it returned to the surface. Buoyancy control had been cracked with compressed air, but there was still the problem of how to maneuver the submarine effectively underwater. Within 5 years, the French had again provided the answer. Give a submarine wings.
A lot of people don't realise that a submarine essentially flies on its hydroplanes like an aeroplane.
The only way it can move in the water, up or down, or through the water, is by being propelled, and by the diving surfaces, the hydroplanes, forward and aft, which tilt to drive you down, tilt up to drive you up.
The French Navy added small horizontal wings to the front of an experimental submarine. They behaved in a similar way to a fish's fins. The submarine's maneuverability was dramatically improved by the addition of these hydroplanes. And all this 10 years before the Wright brothers took off. From now on, submarines could fly. So underwater control has been revolutionized. Though very vulnerable if hit, once dived, the submarine is extremely difficult to find. Yet one of the tools it uses to hide once threatened its very existence. At the end of World War I, submarines ruled the ocean, but then a new invention changed the whole game. Sonar.
Sonar was the underwater equivalent of a radar system, and it performs them very much the same, except radar uses radio waves and sonar uses sound waves.
And sound waves travel 4 times faster and further in water than in air. With the invention of sonar, submarines could be detected by surface ships. But submarine fleets acted swiftly. By 1939, they had their own sonar equipment, and they too used it to find their targets.
Active sonar is when we actually transmit, and we transmit a pulse of energy that will go out through the water as a ping. We've probably all heard it on films. It will hit, be it another submarine, and bounce back, which will give us a range.
As the Battle of the Atlantic raged, the pressure was on submarine designers to invent a device that would defeat sonar. It was German engineers who made the breakthrough with an ingenious cloaking device, rubber tiles. But these new cloaked U-boats became operational too late to affect the outcome of World War II.
Basically, the tiles are a rubber overcoat, and if you're transmitted at by an active sonar, the tiles will, first of all, diffuse and soak up the energy of the transmission made at you.
But even the latest rubber tiles can't make a submarine completely undetectable. By the 1950s, the whole emphasis had switched to making submarines as silent as possible. but that's no easy business.
We are in, for want of a better word, a tin can. Now, anything that rattles or shakes in that tin can is totally magnified, amplified, and will emit a sound out through the pressure hull so that be it other enemy submarines can pick us up.
You build quietness into a submarine with extreme difficulty because the loudest noise that you cure, great, I've cured the loudest noise, I now have a new loudest noise. So it is always a battle to cure the next loudest noise.
This is HMS Onyx, one of the Royal Navy's Oberon class of submarines. Decommissioned now, but when built in 1967, there was nothing else like it.
It was a very quiet diesel-electric submarine, and in electric mode was very, very difficult to detect.
Oberon submarines closely monitored their own noise. They put shock absorbers on machinery to stop vibrations going through the hull and out into the sea. Today, this technique has been taken to a whole new level. This motor is sitting on a metal plate. Sensors have been connected to measure the sound waves transmitting through the metal plate into the water. The noise generated is displayed on these screens. But when a piece of foam rubber is inserted between the motor and metal plate, a dramatic reduction can be seen. In submarine construction, this is known as rafting. Keith Gain served as a sonar operator on Royal Navy submarines. He followed a strict Cold War regime of silence as they sneaked up on Soviet ships.
We would shut down all unnecessary machinery, i.e. fans, anything that's going to make a noise.
Keith used listening devices called hydrophones to eavesdrop on the Russians. Picking up sound in the water like this is called passive sonar.
A passive sonar is where you just want to listen to the information that's in the water around you. We have a ball hydrophone here, which is commonly used in sonar systems. If this was dipped into the sea, it would be very much like a microphone, which you could listen to all the underwater sounds.
Keith and his fellow sonar operators could almost hear a pin drop.
Say if someone in the engine room, for instance, and was doing a repair and he had a spanner and he dropped that spanner onto the deck plates, you would get a crash which would be like banging a drum, basically. And you would hear that for 50, 60 miles away. Contact bearing 220, classified warship.
With passive sonar, Keith's submarine could get a contact and sneak up on an unsuspecting enemy.
We'd have a listen to what was going on, what was being said over the intercoms and communications. And we might pop up the periscope, take a few sneaky snapshots to try and gather more intelligence.
This was a very dangerous game. On one occasion, noise from a chip propeller nearly gave Keith's submarine away.
The whole back end of the submarine was shaking like a dog shaking its tail and resonating a very loud noise.
Keith and his crew were lucky. On another day, this could have proved fatal. Much depended on the sonar operators. They relied on their own skill to distinguish the manifold noises of the sea.
It's fascinating, the sea noises. You have the snapper fish, like that sort of noise. You have the wailing noise of the whale, which is like cries in the ocean. And when you're under the ice, and say at the North Pole as submarines go up there, you hear the ice crunching and creaking and moaning. It's very eerie but very fascinating noise.
In the late 1990s, sophisticated computer sonar analysis was introduced on all Royal Navy submarines. It classifies different underwater noises. It helps the sonar operator make sense of the sounds he hears, each with its own acoustic signature.
You could get, say, a fishing vessel, and it's very fast revving, it's got a high-speed diesel engine in.
Of a merchant ship,
On a warship, it might be.
So the modern submarine is a highly evolved weapon of detection. It uses ultra-sensitive ears for both defence and attack. Submarines in the 21st century are very fast, virtually silent, can go anywhere they like, and need never surface throughout an entire patrol. But these are still not yet perfect machines. The loss of 4 Russian submarines since 1970 highlight the dangers of nuclear power. Even the nuclear reactor may eventually become obsolete.
One day, somebody will have a breakthrough on battery technology. That, combined with fuel cell technology, may very well write the end of nuclear-powered submarines.
In the never-ending search to build the ultimate submarine, others foresee a different future. Not so much changes in technology, but a rethinking of the whole role of submarines.
The submarine of the future will be a mother ship fitted with lots of remotely operated babies. And these babies will have a variety of roles. There'll be mine hunters, there'll be intelligence gatherers, there'll be communications surveyors. So you're going to end up with a highly flexible, multi-role, invulnerable sea control machine. And it's a very exciting prospect.
Relationship between